Well, thank you for the introduction, Marcus. So my presentation will be on the origin of extractable species. I think everyone who has performed an extractable study or has looked at the results of an extractable study of a polymeric device or material may have seen that that may be a long list of compounds. The question then is, where do all these compounds come from? What is their origin, and is it normal that we see what we see in these kinds of studies? It's not only about the scientific curiosity of where these compounds are coming from, or it's not only nice to know information, it's really critical information that helps you understand the risk associated with the choice of materials, and it helps you to mitigate those risks by potentially maybe changing the materials. It can help in the root cause analysis, where is that compound coming from. It can help you fine-tune the analytics for your extractable study, or it can assist in the identification process. In this presentation, like I said, we will be zooming in on polymeric materials. And in this presentation also, you will see a plethora of molecules and structures. I'm sorry for that already. But that will underline how complex and diverse this universe of extractables really is. And it's not only what you put in that potentially may come out. So first, I would like to go back. Like I said, we will zoom in on extractable compounds from polymeric devices. So let's first look at what a polymer is. If you look up the definition of a polymer, for instance, on Wikipedia, it tells you that a polymer is a chemical compound or a mixture of compounds consisting of repeating structural units created through the process of polymerization. For instance, as an example, if the structural repeating unit is ethylene, then you'll have polyethylene, propylene is polypropylene, vinyl chloride is PVC, and so on and so forth. So the word polymer is coming from the Greek words polos, which means many or much, and meros means parts. So it is a molecule that consists of multiple repeating structural units, like I said, and it has a high relative molecular mass and associated properties. And it are exactly those properties, for instance, hardness, shear, density, rheology, tensile strength, and so on, that will need to be fine-tuned to the application that is intended. One good thing that a polymer is only like a spaghetti, a bowl of spaghetti with where the polymer chains would be the spaghetti, and that nothing is in there. But of course, if you look at spaghetti, you have al ragu, you have carbonara, you have pesto, you have marinara. So there are a lot of ingredients that go into a polymer for different reasons, sometimes intentionally, but some compounds will be there unintentionally. So, like I said, some compounds will be added intentionally. These are the typical polymer additives. We will go over that list later on. But some compounds are present because of the production process, or because of the aging of the material, or the aging of the ingredients, or sometimes, things diffuse through the secondary packaging into the drug product, for instance, or may be the result of processing at the end. So we will have a closer look at all those different compounds. First, we will start with the intentionally added substances. These compounds are added to a polymer to improve its functionality or its performance, or to protect the polymer either during the production or during its life cycle, or to have a better processability, for instance, or to change the cosmetic of the material. This is a non-limitative list of polymer additives here, and the additives that are highlighted in blue we will discuss during this presentation. So we will start with the antioxidants. What is their function? It is assuring protection against thermal and oxidative degradation during processing and during the shelf life of the polymer. So you have two types of antioxidants. You have the primary antioxidants, which are the hindered phenols. And these compounds protect the polymer during its life cycle. Those organic phosphites and phosphonates are secondary antioxidants and are added to the polymer to protect the polymer during the processing. For instance, during the extrusion or during the blow molding or injection molding, for instance. Typical examples that you will find as primary antioxidants are BHT, is a very common one, Erganox 1076 and 1010, Erganox 1010. Those compounds will protect the polymer during the life cycle of the polymer. Another example is Ergafos 168. That is a secondary antioxidant, and that compound will protect the polymer during the production process, during the molding, extrusion, and so on. A second class are the plasticizers, and a perfect example where plasticizers are used is PVC. If you don't use any plasticizers with PVC, PVC is very rigid, and I'm referring to the tubes for plumbing here. No plasticizer has been added. However, if you add a plasticizer, and for PVC it can go up to 40% of the total formulation, you end up with a very flexible material. And that can be used, for instance, to make bags out of it. Now, of course, because of the fact that 40% of the formulation of a plasticized PVC is a plasticizer, there are some requirements coming with that. For instance, very low water solubility, stability to heat and light, for instance, during sterilization. And also it needs to have a low odor, taste, and toxicity. I think the most common and most known plasticizer here is DEHP. Of course, this comes with some concerns in terms of it is considered as an endocrine disruptor. So the industry is moving away from DEHP to other alternatives, other plasticizers that have a lower toxicological profile. Another class is our photostabilizers. You cannot avoid from time to time that a container closure system, a pharmaceutical container closure system, or a device may see some sunlight or see some UV light, and that is quite energetic and could potentially degrade the polymer or make the polymer brittle. And these compounds are added. These are typically the sterically hindered amines that to protect the polymer during the exposure to UV light. The typical trade names for that are the tinuvins. Then you have slip agents. Their function is to reduce the friction or film adherence. And that is mainly important when you look at the production of a bag, because the film before a bag is produced is on a roll. Now, these compounds are added to prevent stickiness of that film. So these compounds typically have a very low solubility in the polymer, for instance, polyethylene, and they, as a result, they will be pushed out to the surface, and that's where their action is. There, they will prevent the stickiness of the different films towards one another. As a consequence, because their action is at the surface of the film, they will be readily available and also be seen quite frequently as a leachable. They don't need to migrate out of the plastic. Another example are the acid scavengers. Those compounds are added to the polymer to protect the polymer from acid attacks through the conversion of the strong acid to a weaker acid. An example here is, for instance, hydrochloric acid that is formed during the curing of a chlorobutyl rubber. That's normal. You cannot avoid that. But of course, HCl is very aggressive and can make the material, in this case, the rubber, quite brittle. So in order to prevent that, calcium stearate is added to the rubber, and it converts the strong HCl to the weaker stearic acid. And stearic acid, and together with palmitic acid, is one of the most commonly seen extractables almost in any material that you will investigate. Other examples are pigments, of course, and colorants. Those compounds try to obtain or try to change the cosmetic of the polymer. Sometimes that's desired because you want to differentiate between strength or the application between populations or applications or whatever. And the most common pigments or colorants are carbon black. That makes things black, but there's a concern with polynuclear aromatics there. Or you want to make things white, and that's with titanium dioxide. And every shade of gray in between is the combination of carbon black with titanium dioxide. If you want to color rubbers red, you use iron oxide, or green, for instance, with pigments green 7. You can see I have displayed here a couple of the typical pigments that are also used, that the structure, the chemical structure of those molecules can be quite complex and come with certainly some toxicological concerns. So there's a trend in the industry to use a lower amount of pigments, and also to go away from those more exotic molecules. Clarifying agents or nucleating agents are those compounds that are added to a polymer to make it more transparent. An example, for instance, is polypropylene. Typically, for instance, a box or a container that is used that is produced out of polypropylene is made through injection molding. So you heat up the polymer, you inject it in a mold, and you allow it to cool it off. And during that cooling down process, if you don't have the nucleation under control, the polymer will turn opaque. It will be not transparent. It may turn even white, but by controlling the nucleation during the cooling off of the polymer, you may make the polymer more transparent. And these are molecules that control that nucleation. They are sorbitol based, like NC4 and Milat. So these are the compounds that you potentially will see, for instance, in clarified polypropylene. Fillers are also a group of compounds that you often see. For normal polymers, often that is mainly to reduce the cost, the production cost of a polymer. But for rubbers, it's an integral part of a rubber. Between 40 and 50% of a rubber is made out of filler, inorganic filler material, and that fine-tunes the physical properties of a rubber. For instance, if you have a plunger from a pre-filled syringe, for instance, that needs to be stiffer because of the gliding potential that it needs to have, compared to a stopper on a vial. That will be more flexible and will contain a lower amount of fillers. And these are the typical fillers that you will see that are used, talking about clay, talc, silicates, calcium carbonate, and carbon black. For instance, the reason why the tires of a car are black are simply because carbon black has been added to that rubber. In pharmaceutical applications, carbon black is not often used as a filler material, more as a colorant. Okay, and the last class of intentionally added substances are the catalysts and curing agents. Catalysts give the onset of the polymerization, so it initiates the polymerization. And we see that we have inorganic catalysts, and I have some of the metals that you will see. It may be salts, it may be oxides, it may be complexes of those metals. And I also added a tacticity module. This is mainly to change, for instance, polypropylene from atactic to syndiotactic structures. Curing agents are also added intentionally, and that is mainly to cross-link a certain material and to make a material harder. That is for rubbers, but also for silicon tubing, for instance, or silicon material. There's a whole universe of curing agents and accelerators that is used based upon benzothiazole, sulfonamides, thiorams, and so on. Vultac is a very popular one recently. And they all come with degradation compounds, and we'll discuss that later on. I have put two examples of a peroxide curing silicone. One is the dichlorobenzoyl peroxide, and I think that is the one that you were referring to, Ron, in your presentation also. That leads to the degradation compound dichlorobenzoic acid. And another one is the dicumyl peroxide. So these were the compounds that were intentionally added. Let's now look at the compounds that are not intentionally added. A first class of compounds are those compounds that are degradation compounds from the polymer. Of course, we have added, for instance, antioxidants to a polymer to prevent this from happening. But for instance, if you go to gamma irradiation, this puts so much energy into a polymer that you cannot prevent some kind of degradation from happening. And for instance, acid formation, propionic acid, acetic acid, formic acid can be formed, but also aldehydes, alcohols, ketones, polymer fragments can be formed, in this case from polypropylene. So you have a whole universe of potential degradation products from the polymer. They will be more pronounced in virgin resins that are, for instance, often used in blow-fill seal applications than in polymers that are stabilized with antioxidants. Solvents and monomers, of course, during the polymerization, you use a solvent, and that can lead to traces of solvent residues. I've displayed some of the typical examples that you see: cyclohexane, hexane, decahydronaphthalene, and so on. And of course, as a result of the polymerization process, you will see some monomers. In polystyrene, you may see some residue of styrene, for instance, or in isoprene, you will see in polyisoprene, in rubber. You know, every monomer is related, of course, to its respective polymer. Then you have another class of compounds, and these are the oligomers. Here I have displayed a graph that shows you the distribution of the molecular mass of a polymer. The green line is the molecular distribution of a polymer with an old catalyst system. And the blue distribution is the one with a more recent catalyst. You can see that the distribution is much more narrow with the newer catalysts. And the oligomers are at the left-hand side of that graph. So they are the low molecular weight polymers or compounds that forgot to polymerize completely. So yeah, so that's where you will find the oligomers. Now, I have listed some of the oligomers for different materials that you potentially may see. What is obvious here is that a lot of those compounds are cyclic. So, and that has a reason. Typically, during the polymerization, and this mainly for, true for anionic or cationic or radical polymerization, you have some kind of site of the polymer where the propagation takes place. And when that site is encountering the tail of the polymer, there's some kind of ring closure, and that stops the polymerization, of course, completely. So that's why you see a lot of cyclic compounds as oligomers. Of course, you have those linear compounds also, like, for instance, the ones for polyurethane. These are more the linear ones. And typically, every polymer, every material may have some kind of list of oligomers that are potentially being seen. The polymer additives may also degrade. And here we're given the example of the antioxidants, but also other polymer additives may degrade. But maybe the degradation compounds of the antioxidants are mostly known. Here, for instance, for Erganox 1010, you see that a lot of smaller compounds may result from the degradation of Erganox, but also some larger compounds may originate from the molecule. The smaller ones you will detect with GCMS, the larger ones you will detect with LCMS. And that is the same for Erganox 168. I see that I need to hurry up a little bit. Also, the secondary packaging may play a role, certainly if you have an application of semi-permeable primary packaging. We're talking about ophthalmic bottles or nasal sprays or blow-fill seal applications, for instance. There it is possible that the label that is attached at the surface of the container may release certain compounds that diffuse through the primary packaging into the content of the semi-permeable container. A label is made out of different materials like adhesive, paper, ink, and varnish, and they all give rise to a number of compounds that you potentially may see in the label. That doesn't necessarily mean that everything will migrate through the semi-permeable packaging, but there are certain compounds that are more prone to migration than others. And I've listed some of the examples here. This is an example of an extraction study on the label, just to explain you how complex the composition of a label could be. We see, I think, 46 peaks here being present on the label. An overwrap can also play a role. Also, when it's semi-permeable, that is, for instance, very typical for blow-fill seal applications. It's a multi-layer system where the aluminum is used as the barrier, either for oxygen or for light. And it are those tie layers that keep all these different layers together that is based out, in most cases, out of a polyurethane type of glue. And they will give rise to bislactones that will be evaporated. Typically, the volatile and semi-volatile compounds will be evaporated to the inside of the blister or the overwrap and may diffuse through the semi-permeable packaging into the drug product. And that is the same for the carton or paper box. So you will see potentially abiotic and dehydroabiotic acids or abiotates or vanillin, for instance, potentially migrating through the semi-permeable primary packaging. And a last class of unintentionally added substances are processing impurities. Sometimes you need lubricants in your process, and you want to, they can be silicon-based, they can be mineral oil-based or organic oil-based, and you want to remove them with detergents. Sometimes you see residues of those. You see cationic, anionic, or non-ionic detergents, or sometimes the material is cleaned with a solvent. You can see ethers or isopropanol or methyl ketone, dimethyl ketone. So as a conclusion, It is essential that you know your materials and the composition and its chemistry. It is not what you put in that will come out. And it's not because it's a polyethylene that it's a polyethylene. I mean, every polyethylene will have its different recipe and a different composition and different extraction profile. Some of those compounds may be reactive or toxic, and because of the diverse or the large universe of those compounds, you need a broad chemical screening with a combination of techniques. Knowledge of the materials allows to broaden the scope of your extraction study, and a database can assist in identifying those degradation compounds from all those materials and additives, because otherwise they will be difficult to identify, because most of those compounds are not available in commercially available databases.